Okay, POE kids, we're going to do a little bit of video notes on introduction to electricity. Okay, so sometimes this goes by pretty quick, so hopefully you can stay up with us. So electricity, what is this? The movement of electrons. It's invisible, you can't see it, but it does provide light, heat, sound, motion, quite a few other things. Okay, but it's the movement of electrons. So we're going to get a little nerdy here. We're going to go and look at the very basics of electricity, and we'll go from there. So first of all, you got your elements. Okay, atoms, your smallest piece of an element. And then you've got different components of an atom. You have the nucleus, the center portion of it. You have protons that are positively charged. You have neutrons, they're uncharged atomic particles. So on this one, we talk about atomic numbers, the number equal to the number of protons in the nucleus. The atomic number identifies the element that we're in. So how many protons are in the nucleus? 4. We got 4 red balls there. That's what we're talking about when we go through and do that. Electrons are negatively charged particles. Okay, you can see them right there. They go around in an electrical orbit. And if we did it in two-dimensional, we put them spaced out, it would look something like this. Okay, the valence electrons are the outermost ring of what we have here. Not the inner, but the outermost. Okay, so if we got 2 electrons, the orbit number is 1. If we have the orbit number is 2, then you might have 8 electrons. 3 would give you 18, and so on and so forth. Okay. So what's our valence number in the last one? 8. Those are on the very outside. The orbit's on the very outside to get that out of the way. Let me move my picture. Okay. There we go. Now, electricity at the atomic level, we have electron orbits. They either have 8 or they don't for the most part. Okay, and we're talking about copper in this one. So how many electrons are in the valence? If you count along the outside, there's only 1. So is it a conductor or an insulator? If you know anything about electricity, you know that copper is a conductor. Okay. We'll just continue on here. Sulfur. How many electrons are in the outside? 1, 2, 3, 4, 5, 6 of them. Okay. Is that going to be a conductor or insulator? That's going to be an insulator. Let me go through that. Okay. Now, the electron flow that's the electron from one orbit to another, and they knock each other out. So if we look, it comes in, bing, collision happens, and then it moves on to the next one. Then it's going to seek another one on the next one to it. So if I play the little animation here, it's coming in, bing, it hits, goes to the next one, goes to the next one. So that's what we call the electron flow. Electricity is created as electrons collide, transfer from one atom to the next. Okay? So what are conductors? Electrons that flow easily between the atoms, where the insulators, just the opposite, it's difficult. So if you have 1 to 3 valence electrons in the outer orbit, the insulators are going to be a lot more. Key difference there. Some good examples of conductors are silver, copper, gold, aluminum. That's what wires are made out of. Insulators, mica, glass, quartz. If you think about resistors, rubber, that's an insulator also. Okay. So on this picture, can you identify the conductors? It's the metal portions that we have there on the pliers and then on the wires. So the insulators are going to be the coating around the wires and the coating on the handle of the pliers there. Those are the insulators on there. Okay, you need to know these 3 words: voltage, current, and resistance. Those are the 3 properties that deal with electrical circuit. So voltage is volts. The abbreviation is just V. Current is amps, and that's an A. Resistance is ohms. It's a guy's name, ohms. And it looks like a little horseshoe there. Okay, those 3 help play a huge part in electrical. So what's current? It's the flow of an electron charge. Okay, so if the faucet is off, is there any current? Nope, there's no flow. Now, if you turn it on, is there flow? Yes, there is. Okay, so current deals with the flow measured in amperes. So if we look at this right here, we've got our switch, we've got our battery, we've got a light. Switch off, there's no current, there's no light, but switch it on and the light bulb comes on. Okay, we've allowed the particles to go through on that one. Now we need to talk about conventional current and electron flow. Conventional current is what we thought happens, okay? But it's not really what happens. The electron flow actually goes from negative to positive. Conventional flow says it goes from positive to negative. Now that's kind of confusing, but which one are we going to do? We're going to do conventional current, okay? That's what the engineers use. That's kind of what we do. Scientifically, it's just the opposite. It's the electron flow that would go from negative to positive. But we're going to do conventional current, which goes from positive to negative. Kind of confusing, but that's the way it is. Okay, so voltage, the force. Okay, faucet's off. Is there pressure? Yes, there is. Against the tank, the pipes, against the faucet, it's all there. Okay, when it's on, is there pressure? Yep. Pushes the flow or the current through the system there. Okay, so that's what we mean by voltage or volts. How many volts is it? So again, battery provides voltage that's going to push the current through the bulb, and the switch makes it go on. Kind of gets things flowing there. Okay, now resistance measured in ohms or a little horseshoe there. Okay, what happens to the flow if we stick a rock in it? Well, we've got resistance now. Okay, it's going to plug it up a little bit. The flow decreases, the current decreases. So the resistor is going to prevent the flow or the current from going as fast as it did. Okay, so now we can create resistance. We're going to drop our resistor in there. And what should happen if we turn it on? It's still going to turn on, but it's not going to be nearly as bright. Okay, we reduce the current as it went through there. That's our resistor value. Okay, higher resistor, more blockage. Lower resistor, less blockage. Okay, now to measure voltage, what we have on the right is a voltmeter. Okay, and you have to position it so it reads volts, which is on this side here. Now I've got a battery, it looks like a square battery, so that's usually 9 volts. What we can do is take the leads of it, and if we look at, looks like we're looking at 20 amps right here, or 20 volts, okay? This is millivolts. When we get down here really small, we can go up to 600, but we're going to go a little bit less than 20 there. Okay, and you measure across the component, that means you can turn it in anywhere you want to. Plug it here, plug it there, and you can always measure voltage that way. Okay, you just stick your electrodes or your ends into it, and you find out what the answer is. Okay, so a multimeter can measure volts, it can measure current in amps, it can measure resistance in terms of ohms, depending upon what your switch is at. So if we want to measure current, I'm going to change over here to amps. Okay, and it looks like it's like at 20 milliamps. Now the current must flow through the meter, so we have to break the circuit and stick our leads onto there so that it can read. Okay, if you do not do that and you stick it anywhere you want to, like you did on volts, it will blow up your multimeter. Okay, luckily there's a fuse in there that prevents it from really blowing up, but it'll cost you about $2.50 a fuse. So if you happen to do one of those in class and blow it up because you didn't know what you're doing, you're going to owe me about $2.50 for that one. Okay, but you have to break the circuit, and the circuit has to go through the meter when you do that. Okay, that's the only one where you have to break the circuit. The other one, resistance, and you set it down here in the ohm range. You can see the little horseshoe there. Now, right now it's at 20K or 20,000. and you measure across the component, which means we can measure anywhere we want to. Okay, notice they disconnected the battery. Either turn it off or remove the circuit. But you can measure the resistance anywhere you want to. Okay, so volts and ohms you can put anywhere you want to. If you want to measure the current, you have to be part of the circuit. So be careful on that one. Okay, and we'll stop right there at Ohm's law. So hopefully that helped you. You're going to run through a computer simulation. We do that because you can run it and not worry about blowing anything up. You don't blow up the multimeter or anything like that by measuring different things. So we'll stop it right there. And you have an activity 1.2.3. And let's see if I can get out of here. There we go. And stop.